like high-density polyethylene are thermoplastic examples. And the other type of plastic, which doesn't have this property at all, is called thermoset. And thermoset plastics actually harden upon heating and can eventually break down. They cannot be remolded, okay? These plastics harden upon heating. And, examples of these are we're not going to talk about them, but polyurethanes and silicones. These types of plastics are not very stable to heating. Well, actually, they're stable, but they can't be reformed. Okay. In one case, in the other case, they break down. Don't worry about those properties yet. Silicones are actually great. They're very nice and heat resistant and useful, but you just can't change their shape. Okay. All right. So solvent susceptibility, we sort of talked about it, but the idea is and I'll just make a drawing and talk. But if we had polymer chains like this, you can imagine just looking at a magnified image of your plastic, you would potentially have these interactions between these non-covalent interactions. Sometimes I write faster than I can watch. Non-covalent interactions. These are between polymer chains. And you have you bring in a solvent, and if the solvent can populate around that polymer chain, then it could break that interaction. So instead of having a solid material, then it becomes more liquid as the solvent molecules then intercalate between the monomers and break those interactions. And so that's the idea of solvent susceptibility. Some solvents might come in and be able to do this on certain polymers, but not others. Okay, and so the varying degrees to which you're susceptible to solvents will affect your physical integrity in those solvents. Okay, so another type of interesting property is for these plastics, for example, PLA, their stability to hydrolysis. And many of these plastics that are made by condensation polymerization, of course, can readily undergo the reverse process. So remember, when we brought those two PLA monomers together, we produced water. But if we're around water in the appropriate pH conditions that are highly catalytic for the reverse process called hydrolysis. And so you can imagine you had your PLA. So we had a PLA dimer like this, that we could have a water come in. I'm just going to give myself a little room for my water. And so if these electrons could come in and attack this carbonyl, and it's especially true under basic conditions, so this is very, very base catalyzed, then it's possible for these guys to then pick up a proton from the solvent. And so if you do this, then you'll consume water, you'll use a water, and the water is going to cause a lysis of this chain. And then on the other side, you'll have your other monomer. Actually, sorry, I drew it like that, but just consider that it's an infinite, thing here. So we basically broke. So so it's hydrolysis. So it's like a water lysis, and we broke the polymer. And that's an important property. And so many of these addition plastics are quite stable to hydrolysis, but not to condensation. And so now we'll do a quick clicker question. So get out your clickers and make sure they're set to frequency AA. Hopefully you've already done that. Oh, wait, be careful. Okay, make sure. Okay. All right, some people are clicking in, but be sure you're setting your thing to AA and not just typing AA as the answer. It's okay. You can change your answer, of course. So here's a question. Okay, which monomer likely forms a polymer via condensation polymerization mechanism? It's just very straightforward question. We're just trying to make sure everyone can use their clicker properly here, reinforcing a concept just taught in the previous couple of slides. A minute. Yeah. It should say on the back. Okay. So the answer, who knows the answer? I bet you many of you know the answer. A? Okay. Now, there's one compound on there that we hadn't talked about yet, and it may have thrown you. Maybe if you, I'll stop and look at the data, so people don't cheat. There's no cheating. No. Anyway, most of you did pick A. Let's see, 2% picked B, 3%, okay, whatever. All right, some other people picked the other answers. Somebody picked E. Whoever picked E has to come and talk to me after class. All right. So choice D, you might say, I remember Professor Kresi talking about D, and that's vinyl alcohol, okay, and you guys will be using that in laboratory, not this week, but soon, to make a vinyl alcohol polymer, which is a much more sort of eco-friendly version of PVC. And obviously you have vinyl chloride is choice C, and styrene monomer is choice B. And we know that those all have a double bond system, and they're going to be poised potentially to do condensation polymerizations. Okay. Yeah. Yeah. Okay. So the real question in lab is, the problem that we face in our a civilization-wide problem, a large-scale problem, is we have lots of consumer products, many food, beverage containers, and many other plastics that we come across in our daily lives. And this question is, after we've used them, what do we do with them? And for a while, at least while I was growing up as a kid, they were often thrown away into landfills. And it turns out there's a lot of embodied energy in those plastics, and if they could be recycled and reused, it would be quite good for the environment and would take up landfill space. You know, these things, many of them don't break down so easily. So the question is, though, if you look in your average recycling bin, even though it says, you know, only put in these plastics, you're going to find everything in there: glass, metal, you know, somebody's nasty, snotty napkin, you name it. And what you gross. And what, yeah, and what you learn from this is that there are lots of different plastics. And even if you take a Coke bottle, it's not all made out of PET. The bottle actually has a cap on it that's polypropylene, and that little thing that's left over, that ring, after you unscrew the cap, even if you didn't throw it in the bin, that's made of polypropylene. Okay, so polypropylene is already being mixed with PET plastic, even in the best case scenario. And so what you need are methods to identify and separate these plastics, even in the best case scenario. And of course, we know that that's not how it really is. If you look in the dorm room recycler, you'll see that picture right there, and you'll be like, I can't believe they did that. They just threw the wrong plastic in there. At least that's what I used to think. All right, but now I know it's just reality. So there are these codes that you're familiar with, these SPI resin identification codes that are on the bottom of these containers, and that's where you say, oh, that's a number 1 plastic. And you know, it looks something like this, a symbol with the triangle and the 1, and I'm maybe not going to draw that every time, but that is PET. That's polyethylene terephthalate. And your number 2 plastic is high-density polyethylene. And your 3 plastic is PVC, and so on and so on. 4 is actually low-density polyethylene. Those are your softer, like trash bag materials, your sandwich wraps and things like that. Still polyethylene, but a lower density form. 5 is polypropylene, which is similar to polyethylene, but obviously 3 carbon monomer instead of 2 carbon ethylene. 6 is polystyrene, and 7 is other. And things like PLA fit into other, and hopefully someday there'll be a category for something like PLA if it catches on, so that PLA can be better recycled than just being lumped in with other. But that's how things are today. And you know, that's great, the identification codes, but clearly, you know, even the consumer has trouble. That these bins are filled with different plastics. So really, you need other methods to sort plastics, and that is what you're tasked with in lab next week. And you know, I just want to mention some industrial methods that engineers have thought of over the years to help separate plastics. And so what you do is you take them and you basically grind them up into almost a plastic confetti into little tiny pieces, and those little tiny pieces can then be separated by air and vibrations. You know, this is, I don't know exactly the implication, the exact methodology, but because the plastics have different densities, then they'll tend to float or sink more in a stream of air, okay? And so heavier plastic bits will separate to one side of this air vibrating apparatus than lighter plastics. And plastics that are somewhere in between will sort in the middle. And so you can sort all these little plastic pieces by this air vibration technology. And obviously it's a lot more complicated than I just said, but you can also you can use electrostatics, and these little pieces can take on certain numbers of charges depending on the type of polymer. Okay, and then you can have basically charged plates, and these plastic particles can be separated based on how charged they are, which is a unique property of each type of plastic. So that's an electrostatic separation. And another sort of, imagine using liquids of different density. And again, to separate by density, separate plastic bits by density. That's what we're talking about doing next week in lab. And you can imagine, you have a situation like this. First of all, density. The idea of density is mass over volume. So mass in grams and say volume in milliliters. And based on how much liquid a volume of plastic will displace, if that plastic bit is heavier than that volume that's displaced, it will tend to sink. If it's less, then it will float. Okay? And it's Archimedes' principle. You have a beaker, and you have some solution of known density. You could use some examples: salt water, regular water. See, if you put salt in there, seawater is more dense than regular water. You can make it higher density. And some organic solvents, say, for example, ethanol. Ethanol is less dense than water. Okay, if you had, say, solvent, you could have a solvent like glycerol, which is really, have you ever seen glycerol? It's extremely dense relative to water. So you could try different solvents, and you could put your plastic bits up there. I'm going to make these different colors for fun so that you can illustrate a point. And you start them out up here at the beginning, but it turns out that the red guys are more dense than the blue, and the red guys are more dense than the solvent, and the blue is less dense than the solvent. Then they will separate. And then what you just use is some sort of skimmer. You have some sort of device that you can come in and then skim. You can skim off the blue guys, and then you can, say, suck out the red guys from the bottom, and then recycle the solvent, the solution that you have in there, and then do another separation. And so this technology works well in cases where the blue and the red plastics differ in density. If they have the same density, then all bets are off. And the method also will have problems if, say, red and blue are both less dense in the solution, then they'll both float, or they're both more dense in the solution, then they'll both sink. So then you need to select appropriate solution to do your separation. So those are really the questions that you're confronted with in laboratory, and that's what you'll think about: is how will you separate now, say, 6 different plastics from one another. And I ended about 5 minutes early, so I can now entertain questions, or any questions? You guys like to get done early? Okay.